Good day, everyone. Today we will talk about the temporal logic and the XOR recurrence relation in Tau. Study notes. The formula is an example of a temporal specification in the Tau language. Tau is unique because it treats software as sentences, meaning mathematical and logical statements are directly executed as programs. When you execute this formula, you are defining a small, perpetual machine that generates a repeating sequence of true and false values based on a logical pattern over time. This Tau specification is an example derived from the Tau language demo developed by the Tau team. The ongoing implementation of the Tau language is available in GitHub, where demonstration files are provided to show how to use the language. The entire statement begins with the command R, which stands for run. This tells the Tau system to execute the program chronologically, starting at time step t is equal to 0. Part 1. Deconstructing the structure, time and streams. So you can see I highlighted the O. O means output. So this is a stream. This is an output stream. So when you see O, it means output stream. Think of it as a continuous tape recorder where the program writes its output, a sequence of ones and zeros, as time progresses. Have you observed something? There is no input stream, right? It's all output stream. Execution without an explicit input stream. The Tau specification, or this specification, does not contain an explicit input stream. Tau is able to execute this specification because Tau programs do not strictly depend on input streams to execute, as long as the specification is satisfiable. The nature of specifications and execution. Tau is a software specification language. You do not write a program in Tau, but a specification, which effectively represents all programs that meet it. The entire formula is directly executable as is. Satisfiability requirement. Before a specification is run, it is checked for satisfiability. A specification is satisfiable if, loosely speaking, for all inputs at each point in time, there exist outputs that meet the specification. Execution as solving. Execution is the process of receiving input values, plugging them into the specification, and then solving for the missing output values. Why input is not required here? A self-contained recurrence. This specific formula relies entirely on initial conditions, like this one. So this reads as output 1 at time 0 is equal to 1 and output 1 at time 1 is equal to 1. This is the initial conditions. And also the orange shades is the own previous outputs. So these two are to determine the next output. Deterministic output. Since the output is entirely determined by internal recurrence, there are no unquantified input variables for the interpreter to request. Program synthesis. The system can synthesize a program, the output sequence, that adheres to this satisfiable self-contained specification. This demonstrates that a specification only requires an input stream if external information is logically necessary to define the next output. If the specification provides sufficient constraints to determine the output indefinitely without external input, the system proceeds with execution based on its internal logic and recurrence relations. Time markers. Imagine this is the violet one is the output one at time t refers to the value being calculated right now at the current time step t. Output 1 at time t minus 1 refers to the value calculated 1 moment ago. And output 1 at time t minus 2 refers to the value calculated 2 moments ago. This dependence on past output is a key feature of temporal logic called bounded lookback. Logical connective. The 2 ampersand symbol is the logical conjunction logical AND operator, which joins constraints. All parts of the formula connected by this 2 ampersand must be true for the specification to be satisfied at every time step. Logical values ones and zeros. In Tao's foundational logic, which is based on Boolean algebras, a system of logic concerned with true and false, the values 1 and 0 are used. 1 represents true, the top element, and 0 represents false, the bottom element. Part 2. The core rule. The XOR recurrence. The most crucial part of the formula is the mathematical operation, which is defined by the core rule and the initial conditions. The operator plus is exclusive or XOR. In the context of Boolean algebra used by Tau, the plus symbol is defined as the exclusive OR function, also known as the ring sum. This is not standard arithmetic addition. The XOR rule only returns true if exactly one of the inputs is true. So I have here a table which has the input 1, input 2. We will perform an XOR operation and we will describe it. So here, this truth table, input 1, 0, input 2, 0. The result would be 0. No inputs are true. Input 1 is 0. Input 2 is 1. So the result of this would be 1. Exactly one input is true. Input 1 is 1. Input 2 is 0. Again, the result is 1 or true because exactly one input is true. And if both the inputs are true, the result is false or 0 because both inputs are true, not exclusive. The recurrence relation. The overall formula defines a recurrence relation, meaning the program output is defined by previous outputs. The initial conditions, the starting values. See, this is the initial condition. Output 1 at time 0 should be 1. First initial condition. Another initial condition is when the output 1 is at time 1, it should be the value of it should be 1. Okay? So these are the two initial conditions or starting values. The next is the continuing rule. So this is the continuing rule. Output 1 at time t at the present time is equals to output 1 at time t minus 1 and output 1 at time t minus 2. So since this is with a plus, this means XOR. We will XOR this input 1 and input 2. The current outputs is the XOR of the two outputs immediately preceding it. Part 3. Step-by-step execution. The sequence. So when the tau system runs the program, it uses the initial conditions and then applies the XOR rule recursively. So in this table, we have the time at t, input 1 at output 1 t minus 1, input 2 at output 1 t minus 2, the XOR operation or calculation, and we will show here this column, the output 1 at time t, the result. I'll also show you the formulas here. So again, the blue shades, these are the initial conditions. Okay, let's start. So at time t is equal to 0, I highlighted here that the initial condition here in this tau specification is output 1 at time 0 should be 1. So we expect this one to be 1. Okay? Because this is the initial condition set in the tau specification. So here, it's not applicable. 1. Immediately 1 here. And the second initial condition here is says output 1 at time 1 should be 1. So here, this should be 1 also. Here, neglecting this one. No need this one yet. Okay. Now let's go to time t is equal to 2. Now that the time t is the initial conditions have already done their part, so I'll just don't don't think about this anymore. So let's focus our attention to this one. So now we will fill up this value. So input 1, output 1 at time t minus 1. Okay, so what is the value of this one? So we'll just replace the t to 2. So here, this is t, this becomes 2. So that is 2 minus 1 is 1. So the value of this input 1 should be output 1 at time 1. Here, this one. Right. Because it's the time now is time 2, right? And then 2 minus 1 is 1. So this is it here. So go here. And the next thing is here. So output, we'll try to know what is the value of input 2 by getting this one. So output 1 at time t minus 2. So here, since t is 2, so 2 minus 2 is 0. So we know the output 1 at time 0 here is 1. So this one will go here. This. Okay. And now we have we will calculate the XOR. So the XOR of these two. So 1 XOR 1, as we recall, should be 0. Right? You XOR the input 1, XOR input 2. So 1 XOR 1 is 0. So the output at time t, the result is 0. Okay. Let's now go to time 3. Again, the same process. What happened a while ago? Um, we don't care anymore with the initial conditions because they have already done their part. Okay. The initial conditions are just for at time 0 and at time 1. Now we will always focus here. Okay. So here is output 1 at time t minus 1. So now the time is 3. So 3 minus 1 is 2. So output 1 at time 2. This one. Right. So this is 0. Go here. And next is the input 2. Let's know the value of input 2. Input 2 is just you replace t to 3. So 3 minus 2 is 1. So output 1 at time 1. Time 1 is this. Right? So go here. 1. And now let's go calculate the XOR of input 1 and input 2. So when you XOR 1, when you XOR the input 1 is 0 and input 2 is 1. So 0 plus 1 is 1. Here. So the result here is 1. Okay. Next is at time t is equal to 4. Again, same. He'll just replace this by 4. So 4 minus 1 is 3. So output 1 at time 3 is 1. So you'll just go here. And here, replace this one to 4. Output 1 t minus 2. Replace this by 4. So becomes output 1 at 4 minus 2 is 2. So should be output 1 at time 2. This one. So 0 going here. And we know that when we XOR 1, XOR 0, that will be 1. Here. Okay. Let's go to time 5. So at time 5, again, 5, we will just replace t equal to 5. So here, so 5 minus 1 is 4. So output 1 at time 4 here. So go here. And here, this one is output 1 at time 5 minus 2. So that is output 1 at time 3. So here is output 1 at time 3. So this go here. Over here. Okay. And now, we know that if both the two inputs are 1, when we XOR that, that would be 0. 1 plus 1, 1 XOR 1 is equal to 0. Yes. And if you continue all along, the result is a perpetually repeating Boolean sequence. So 110, 110, 110, dot, dot, dot. Part 4. Executing the XOR recurrence in the tau REPL. The preceding steps provided the rigorous logical blueprint for a program in the tau language. But tau is unique because these requirements and constraints are not just theoretical documents. They are executable specifications. To transition from the mathematical abstraction of XOR recurrence to a running program, we must utilize the primary interface for interacting with the tau language, the tau REPL or read, evaluate, print loop. This demonstration inside the tau REPL, which is a command line application, shows the concept of program synthesis in action, where the system executes an automatically chosen program that satisfies our logical formula. We analyze the formula. As we see a while ago, the initial conditions are the blue shades. The output 1 at time 0 is equal to 1 and output 1 at time 1 is equal to 1. These are the initial conditions. And the orange shades are the own previous outputs. At output 1 at time t minus 1 and output 1 at time t minus 2. To see this formula generate the sequence 110, 110, dot, 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 in the environment provided by the tau team, we follow these two crucial steps in the tau REPL. Step 1, declaring the output stream. SBF output 1 is equal to console. The tau interpreter must know what type of Boolean algebra the stream O1 belongs to, as this determines the output format. By explicitly declaring the stream O1 as a simple Boolean function or SBF type connected to the console, we ensure the output displays the results using the constants 1 and 0. Without this declaration, the stream defaults to the tau type and the output uses T and F. The explicit SBF type gives us the numerical ones and zeros from the Boolean algebra. Step 2, running the temporal specification. Now we execute the formula using the run command. The interpreter reads the instruction, checks for realizability, ensuring that for all inputs, an output exists that meets the specification, and then begins generating the sequence step by step, using the historical output to calculate the present output. The system output would then iterate through time steps t equal to 0, 1, 2, dot, 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 continuously displaying the result of the XOR recurrence. This table shows the time step, the output, and our interpretation. Let's recall what we did a while ago as we see here. So at time step 0, the output is 1 right here, initial condition. And the initial condition again at output 1 at time 1 is 1. And then at time step 2, the output 1 at time t is becomes 0. Why? Because we XOR the input 1 and input 2. Sorry, here. Input 1 and input 2. So 1 plus 1 is 0. That is 0, 0. Yeah. 1 XOR 1 is 0. Sorry. Time step 3, the output is 1. Why? Because when we calculate the input 1 is 0, XOR input 2 is 1. So 0 XOR 1 is 1. That's why it's 1. Time step 4, again, the output is 1. Why? Because when we calculate input 1 is 1 and input 2 is 0, 1 XOR 0 is 1. That's why it's 1 here. And time step 5, it's becomes 0. Why? Because the input 1 is 1 and input 2 is 1. So 1 XOR 1 is 0. And that keeps on repeating. Sequence continues 110, 110, 110, 110, 110. Dot. This live execution in the REPL demonstrates how declarative specifications stating relationships rather than machine instructions are the executable software itself in the Tau language. Part 5. The benefits of logic. Why this is important. While this specific example generates a simple repeating sequence, the underlying mechanism is central to the goals of the Tau language. Number 1. Correctness and certainty. Because the specification is rooted in rigorous logic, the first order theory of atomless Boolean algebras, the system can formally and automatically prove assertions about the code. This enables proof of correctness for all software operations in finite time. The Tau system is designed to be decidable, meaning it is always possible to answer any expressible question in finite time. Number two, software synthesis. The formula is not just a description, it is the actual program. If a specification is satisfiable, meaning that for every input, an output exists that meet the spec, Tau can automatically synthesize the program that meets those requirements. Number three, foundational power. This recurrence relation demonstrates the capability of the Tau language to describe complex processes through simple logical constraints, which scales up to allow for things like specifying systems in their entirety, or even specifying software that can reason about its own sentences. Self-referential logic. This logical foundation is necessary for creating truly safe AI. Number four, scaling collaboration. This unambiguous form of logic is the basis for scaling human discussions. By having users express their opinions and requirements as formal, logical statements, the system can detect the consensus score and enable collaborative software development. The power of executable logic. What we witnessed with this formula is the principle of software as sentences in action. This small temporal specification executed seamlessly whether using the default Tau type or the explicit SBF type demonstrates Tau's ability to define and execute programs entirely through decidable logical constraints. The logical rigor we explored scales up to solve critical, long standing problems. Number one is decentralized control. Tau is the only proposed framework that aims to deliver a blockchain fully defined and controlled by its users. The system is built to change itself according to the totality of desires of its users. Logical AI breakthrough. Tau achieves a form of logical AI that allows the language to speak about its own sentences, necessary for self-amendment and defining the law of changing the law, sidestepping issues that defeat conventional formal systems. The endgame. Because the system can continuously evolve and become anything its users want it to be, it is heralded as the endgame of all blockchains. The Tau language is not merely a theoretical exercise. It is the technological foundation for advancing humanity by scaling collaboration using logical AI. The project roadmap indicates a clear path forward and soon releasing the alpha testnet. The alpha testnet is intended to be the first demo of the language's capabilities, and it will be a proof of concept network that adapts to user requirements block by block. The success of Tau relies fundamentally on collective participation, as the users themselves are going to set the rules of the network. You can contribute by familiarizing yourself with the logic to use the innovative feature of the testnet and affect the block acceptance conditions Users will need to learn Tau and write logical formulas. Getting familiar with first order logic and Boolean algebra is highly advised. You can also contribute your brain power. While the project is not working alone, there is still plenty of room for contribution. The intellectual input from community members, your brain contribution, is also considered economically significant. We encourage you to become a community member and play an active role in shaping the future of this groundbreaking technology. This technology offers the promise of collaborative decision making in large scale, a technological breakthrough orders of magnitude greater than the original blockchain innovation. We invite you to follow the development and contribute to what many believe is the only hope for humanity's survival against the risks posed by centralized, misaligned AI. Temporal logic and the XOR recurrence relation in Tau. Study notes. Thanks for watching.